And I bet you're starting to feel that familiar panic setting in. We'll take a deep breath, because today we are going to instantly cure your board exam fears. We're taking one of the most notoriously dense physics topics out there, the magnetic effects of electric current, and we're breaking it down into an easy-to-digest, highly visual masterclass. By the end of this, you aren't just going to memorize the concepts. You're going to completely, absolutely understand them.
Here's our roadmap for mastering this stuff today. We're going to cover magnetic fields, how electricity creates magnetism, solenoids and electromagnets, magnetic force rules, and finally, domestic circuits. Let's get right into it.
Section 1. Magnetic fields. Visualizing the invisible.
So, before we even touch the electricity part, we really need to understand a magnet's territory. You already know a magnet naturally attracts objects made of iron, nickel, and cobalt. And just like a politician claiming an area of influence, a magnet has a region around it where its magnetic force can actually be felt. That region is the magnetic field. And hey, if anyone ever tries to use the classic pickup line on you, "Are you a magnet because you attract me?" just remember the ultimate Sigma reply, "I'm not a magnet, I'm just iron, and you're automatically attracted to me." Anyway, to visualize this invisible territory, we use magnetic field lines. Now, these lines form completely closed continuous curves. Outside the magnet, they always, and I mean always, travel from the North Pole to the South Pole. But here's the trick. Inside the magnet, they actually travel in reverse, from south to north to complete the loop. And how do we know where the magnet is strongest? Just look at the lines. The closeness of the lines indicates magnetic strength. Think of it like a crowded concert, where people are packed tightly together right near the stage. The energy is at its absolute highest. That is exactly how magnetic poles work.
All right, let's pause our rapid pace for just a second. I'm going to ask you an extremely common high-yield board exam question. Why do magnetic field lines never intersect or cross each other? Really think about it. What would physically have to happen if two lines suddenly crossed paths?
It all comes down to what I call the compass contradiction. You know that a compass needle aligns itself to point in the direction of the magnetic field, right? Well, if two lines intersected at a single point, and you placed a compass exactly on that intersection, the poor compass needle would have to point in two completely different directions at the exact same time. And that is literally, physically impossible. It's kind of like those math proofs where you assume the opposite is true just to prove how ridiculous it is. Lock this logic in, guys. It is a guaranteed exam point saver.
Moving on to Section 2. Electricity creates magnetism. The ultimate plot twist.
Up until now, we've just been talking about normal chunks of metal. But here is the massive plot twist. Scientists discovered that we can actually create these invisible magnetic fields on demand using electric current. This whole idea started with Hans Christian Ørsted. He was doing a totally normal electrical circuit experiment, probably just poking around the lab with some friends, which honestly is how the best breakthroughs happen. He accidentally placed a compass near a live wire, and when he flipped the switch, the compass needle suddenly deflected. It was like magic. He added more batteries to increase the current, and the deflection got stronger. He reversed the battery, and the needle deflected the opposite way. With that one accident, he had just proved that electricity directly creates a magnetic field.
Okay, so how do we know the direction of this newly created magnetic storm? Well, we use a super simple physical trick, Maxwell's right-hand thumb rule. I want you to literally lift your right hand right now. Come on, do it. Point your right thumb straight up in the direction of the electric current. Now, curl your forefingers inward. That circular curling motion, that is the exact direction of the magnetic field wrapping around the wire in concentric circles.
All right, Section 3, solenoids and electromagnets. Weaponizing the trick.
Once scientists realized they could literally summon magnetic fields using just simple wires, they definitely didn't stop there. They figured out how to amplify Ørsted's trick to manipulate heavy machinery. The core technology behind amplifying this magnetic field is called a solenoid. A solenoid is just a coil of many circular turns of insulated copper wire wrapped tightly like a cylinder, kind of like a giant spring. When you push current through it, all those tiny magnetic fields from each individual loop combine their forces. The result? The entire coil behaves exactly like a bar magnet with a distinct north and south pole. And here is the secret sauce. If you stuff a soft iron core directly inside the spring-like wire, you supercharge it, creating a massively powerful electromagnet.
You can basically consider this your ultimate exam cheat sheet. I mean, why go through all the trouble of making an electromagnet when permanent magnets already exist? Well, because electromagnets give us control. They're temporary. You can turn them off, dropping a heavy car in a scrapyard with literally the push of a button. Their strength is completely adjustable just by giving them more or less current, and brilliantly, you can reverse their north and south poles just by flipping the battery around. A permanent magnet, It's always on, fixed in its strength, and rigid in its poles. In physics and in life, control is power.
Next up, Section 4, Magnetic Force and Hand Rules, the climax of force.
So we know a live wire creates a magnetic field, and we know a permanent magnet has a magnetic field. But what happens if you put a live wire directly inside a permanent magnetic field? The two invisible magnetic forces clash, and they physically push or pull the wire. We just created motion. But again, how do we predict which way the wire will actually move? Switch to your left hand for this one. We're going to use Fleming's left-hand rule. Stretch your left thumb, index finger, and middle finger out so they are all strictly perpendicular to each other, like the corner of a room. Now, here's the brilliant mnemonic to remember this. Father, mother, children. Your index finger is mother for magnetic field. Your middle finger is children for current. And your thumb is father for force. If you align the mother and children to your circuit, your thumb will perfectly point to the exact direction the wire will be physically pushed.
Now, you really got to watch out for this tricky conceptual trap on your exams. The physical force isn't just about the current itself, it's completely dictated by the angle. If your current wire is sitting at exactly 90 degrees, so perpendicular to the magnetic field, boom, you get maximum force. But if you align the wire perfectly parallel to the magnetic field lines, at 0 or 180 degrees, the forces just slide right past each other. You get absolutely zero force. The wire stays dead still. Don't let them trick you on this on test day. Finally, Section 5, Domestic Circuits, bringing it home.
We've talked a lot about high-level physics, invisible forces, clashing fields, the whole shebang. But how does all this electric current actually, safely, power the screen you're watching this on right now? Well, the crucial point here is understanding why our homes use parallel connections instead of series connections. Imagine if your house was wired as a series circuit. If one single light bulb burned out in the bathroom, your entire house would go completely dark. Parallel circuits save us from that nightmare. In parallel, each appliance gets the exact same potential voltage. Every TV, fridge, or smart bulb can be switched on and off totally independently. And it seamlessly handles massive devices, like your air conditioner, alongside a tiny phone charger at the exact same time.
Let's look at a very real-world application. If you've ever peeked behind a wall outlet, you'll see a very specific wire color code. Red is the live wire. It brings the dangerous high-energy current from the station straight to your house. Black is the neutral wire. It calmly returns the current to complete the circuit. And green is the earth wire. That green wire is your absolute ultimate bodyguard. If any charge leaks onto the metal body of, say, your fridge, the green wire instantly dumps that deadly electric shock directly into the ground outside, literally saving your life.
Okay, we've broken down fields, electromagnets, hand rules, and home safety. You have the exact roadmap you need to ace these concepts on your exams. So I'm going to leave you with this final thought. The next time you walk into a room and casually flip a light switch, can you picture the invisible magnetic storm you just unleashed inside your walls? Keep that curiosity alive, keep visualizing the concepts, and you are absolutely gonna crush it. Thanks for joining this explainer.